In this video, we're going to learn about some important addition reactions of alkenes. We said alkenes are a lot more reactive than alkanes. They can do a lot more than just burn. Being flammable is pretty cool, but alkenes have a lot more reactions in addition to just, burning them to make CO2 and water. So the first reaction we're going to learn about is addition of hydrogen, called hydrogenation. And the addition of hydrogen or hydrogenation is really used to convert alkenes to alkanes. So, let's just put it up here. This is how alkenes get converted into alkanes. This is how double bonds go to single bonds. So in hydrogenation, we start off with an alkene and react it with H2 or hydrogen, but diatomic hydrogen. We said hydrogen is one of those elements likes to come in twos in its elemental state. Remember, we like to recall I brought chlorine for our new hot tub. It's the H for hot tub. The hydrogen is diatomic. And then it requires a metal catalyst. What could that metal catalyst be? Well, that can be something like platinum or palladium. In catalytic converters in cars, it can also be rhodium. It can be zinc. So this is the way a catalytic converter hydrogenates in your car as well. And so, and complete products of combustion can be alkenes that require hydrogenation in that catalytic converter. And the metals in them are pretty valuable, whether it's platinum, palladium, or rhodium. Sometimes they're stolen, cut out of cars because people want to resell them for the expensive metals that are actually the catalysts in those catalytic converters. So it's kind of fascinating. Anyway, that hydrogen gets added across the double bond. So it really gets split, essentially in one hydrogen ends up on each side of the double bond. And it requires this metal catalyst to get the job done as well. So we're adding hydrogens across the double bond. We need a metal catalyst. And we go from having an alkene to just a simple alkane. So what's an example of hydrogenation? What about ethylene? What about our C2H4? So we have our carbon-carbon double bond, and we have two hydrogens on either side. And essentially, we're going to add hydrogen, or H2, across that double bond. We could use a catalyst like palladium, for example, to add those hydrogens across the double bond. The catalyst really weakens the hydrogen to hydrogen bond, allowing that double bond to go ahead and react with the hydrogen. It really occurs right on the surface, right on kind of that rough surface of the metal is where this is happening. And so essentially, you're getting one hydrogen on each side of that double bond added across, what I call across the double bond. Okay, the second reaction we're going to talk about is hydration, or the addition of water across the double bond. So think of hydration just like we talk about in everyday life, about being hydrated, having enough water to drink. That's the same thing. We're going to give this double bond some water to drink, if you will. It's helpful to think of water for the purpose of this reaction as HOH, just like it was helpful in acid-base chemistry. It's pretty helpful here as well. So we're thinking of breaking that double bond so that we just have a CC single bond. We're thinking of breaking that HOH bond, if you will, so that hydrogen adds on one side of the water molecule and the OH of water, hydrogen adds on one side of the alkene and the OH of the water adds on the other side of that alkene. So, for example, in ethylene, we have C2H4, we have that CC single bond. We're going to break, that CC double bond, rather. We're going to break that double bond so that we only have a CC single bond. And we're going to split that water molecule so that H is on one side of the double bond and OH ends up on the other side of the double bond. Now it's a single bond. So then we end up with, CH3 and CH2OH for ethanol. Now, it's important to note that in both cases, in both our general example and our specific one, we've got an acid catalyst. So we really need an acid over that arrow acting as a catalyst. We're going to see an acid catalyst. We can see a specific acid, like here we've got H2SO4 or sulfuric acid. Maybe they put H plus over the arrow to specify that we had an acid catalyst, or even H3O plus, the hydronium ion. All of those things, would signify to us that we've got our acid catalyst that we need for that hydration to occur. Okay, so we're going to look for examples of these two main types of reactions. So here in this first example, we've got CH3CH double bonded to CH, and then single bonded to CH3. And then it says plus H2/Ni, or hydrogen and nickel, right? So we've got hydrogen. We've got nickel here is going to be our metal catalyst. So what we're seeing is hydrogen and that metal catalyst, or an example of hydrogenation. Okay, so hydrogenation is looking for that hydrogen and looking for that metal catalyst. So what alkenes typically do is we break that double bond and we make a single bond. So we'll write out our CH3. We'll end up with, we've got that bonded to a CH. Now, instead of a double bond, next we'll change it to a single bond. We'll break that double bond. So basically, we're copying the whole molecule, the 4-carbon chain, and all of its hydrogens, but now we've got a single bond in place of our double bond. And then we're going to add these 2 new hydrogens across where the double bond used to be. So we have our added hydrogens here across carbon 2 and carbon 3, because we had that double bond right there in the middle. Okay, so hydrogenation. Hydrogen, a metal catalyst, breaks the double bond, adds the hydrogens across the double bond. Okay, next up we have the same molecule, CH3, CH, double bond, CH, CH3, but we're going to add water, and it says there's also /H plus. Okay, so H plus was our code for acid, right? We've got that proton, we know there's acid present. And water can act like HOH and add across that double bond. So again, first things first, when we're copying our molecule, we're going to copy the whole thing, CH3, CH, but instead of a double bond, we're going to break it. It's going to be a single bond. CH and then a CH3 out on the end. And go back to our middle bond where it used to be a double bond. We can add H on one side and OH on the other. Now, it really doesn't matter if we add the OH to the second or the third carbon, because we would have the same molecule either way. In fact, we could have added the OH to the second carbon and added the H to the third carbon, and we would just have the exact same molecule. You can flip them and superimpose them right on top of each other, exact same molecule. So that part really doesn't matter. But there'll be something different with this last one. So in this last example, we've got CH2 double bonded to CH, single bonded to CH2, single bonded to CH, and then that last CH is single bonded to 2 CH3s in the carbon chains. So it's really this double bond at the beginning of the molecule that is important. And it says it's reacting with water and H+. So again, there's our acid catalyst, our H+. And water is again going to act like HOH and add across in hydration. Okay, so we've got an example of hydration. So we're going to copy down our molecule. We've got CH2, but this very first bond is going to convert to a single bond. We've got CH, then we can just start copying. CH2, CH, and then there's 2 CH3s on that last CH. Now, there's going to be an important rule here. It really didn't matter where we added the OH, if we added it to the second or the third carbon, because it was a 4-carbon chain, it was going to end up on carbon 2, essentially, no matter what. But in this molecule, it matters because here we could be adding the OH either to the first carbon that has 2 hydrogens and is bonded to one other carbon, or we could be adding it to the second carbon, which has 1 H and is bonded to carbons in either direction. And there's a special rule for this. It's actually called Markovnikov's rule. Knowing the name of it is not so important as knowing how it works. Markovnikov's rule basically says that we add the H to the side of the molecule that has more H's already. It goes with its friends. Add the H to the side with more H's. Now, it's because the organic chemists have studied how this reaction works, and we've really figured out that this makes a more stable intermediate product. So if you're interested in studying why that is, you got to take more organic chemistry so we can teach you all about it. But the gist of this is, here this carbon in the end that already had 2 H's is the one with more H's. So that's the one we're going to add our H to. We're going to add our hydrogen to the carbon that has more H's, and then our carbon in the middle with only 1 H will get our OH. And that is what we call Markovnikov's product here. So we are going to make the Markovnikov product by adding the hydrogen to the side that has more hydrogen. So in summary, for hydrogenation, look for adding hydrogen with a metal catalyst like nickel or platinum or palladium, even rhodium perhaps. And then in hydration, look for an acid catalyst, a specific acid, or just H plus or H3O plus. And then look for that water that you're going to add as HOH so that you get 1 alcohol in the end on your product.